Before we take a look at implicit differentiation, let us first discuss higher order derivatives. So we know that f prime, this is the derivative of some function f. If we derive this again, so we get the derivative of f prime, we write it in short as f double prime. This is the second order derivative of f. Or in short, the second derivative of f. So if we do this in Leibniz notation, we obtain the following. So we had y is some function f of x. The derivative of y to x, dy dx, is your first order derivative. If you derive it again, then you get the second order derivative, so d dx of my first order derivative. To write this in short, this is d squared of y divided by dx squared. So the second derivative of y 2 times derived towards x. And then we can continue. So we have the second order derivative. If we derive again, we get the third order derivative. Please note that here we write this as a 3 between brackets. So this is the third order derivative of f. And then it continues. So the third order derivative derived gives me the fourth order derivative, and so on. For certain functions, you can in this way find a general formula for the nth derivative of the function. So we have a function f of x, and the goal is then find an expression for the nth derivative of my function f of x. And we'll do this for 3 examples. So the first one, we take f of x equal to the sine of x. The second one, take f of x equal to x to the power minus 1, so the inverse of x. And then the third one, f of x is the root of x squared plus 1. So try to find an expression for the nth derivative yourselves before continuing with looking at the solutions. So what you will do is you will take a first order derivative, second order derivative, third order derivative, and then you will try to see if you find a repeating pattern, and you will try to write down the nth derivative as a general formulation using the pattern that you observed. The first function we had was the sine of x. If we then look at the first order derivative, so f prime of x, we know that the derivative of sine of x is equal to cosine of x. For the second order derivative, we derive the first order derivative. So this is the derivative of cosine x, which is minus the sine of x. We do this again. So the third order derivative of x is the derivative minus sine of x, will give me minus cosine of x. The fourth one will again give me the sine of x, and so on. So what we see is that we have a repeating pattern, sine, cosine, and that the sign, so the plus or the minus sign, changes in every 2 steps. We can thus write in general that the nth derivative of f of x is either a sine or a cosine, depending on which iteration we are at, and the sign of it will be positive or negative depending on which iteration we have. So what we see now is that if n is even, so we have an even order derivative, here the second derivative, fourth derivative, and so on. In that case, we have sine of x as a derivative, but with a factor minus 1, which changes. So how do we incorporate this? If n is even, this means that n is 2 times k, and we have minus 1 to the power k. So if n is 2, k will be 1. We have minus 1 to the power 1, it's negative. If n is 4, k will be 2. We have minus 1 to the power 2, it's a positive sign, and so on, and so on. And then we can do the same thing for the odd one. So if n is odd, then we write n is 2k plus 1. And we get the same formulation. It's minus 1 to the power k times the cosine of x. And so this will be the general expression for the nth derivative of my function. If we do the same for the inverse of x, so x to the power minus 1, my first derivative of x is minus 1 times x to the power minus 2. For the second derivative, we will keep the notation, it's minus 1 from the previous, times minus 2 times x to the power minus 3. The third one, this becomes minus 1, minus 2, minus 3 times x to the power minus 4, and so on. So if we want to compress this expression, if we want to simplify, what we see, this is minus 1 times x to the power minus 2. Here we have two minuses, so this becomes plus, and then you have 1 times 2, so this is 2 factorial. 1 is also 1 factorial, and here you have x to the power minus 3. The next one is negative again, so this is minus 3 factorial, x to the power minus 4. And so you see that there is a general pattern emerging, a general pattern which allows us to write the nth derivative of x as minus 1 to a certain power. So we see it alternates between minus and plus. The odd ones are negative, the even ones are positive. So it's just minus 1 to the power n times the derivative. So the order of the derivative factorial. The first derivative had 1 factorial, the second derivative had 2 factorial, the third derivative 3 factorial. So here it will be n factorial. And then this multiplied with x to a certain power. We see that if it's the first derivative, the power is 2, the second derivative, the power is 3, and so on. So the power is n plus 1, but then the negative power, so minus n plus 1. Let's now do the same thing for the final example. So we have the root of x squared plus 1. For the first derivative, so f prime of x, we apply that the root is the power 1/2. So this is actually x squared plus 1 to the power 1/2. So this is 1/2 times x squared plus 1 to the power 1/2 minus 1, so minus 1/2, times the derivative of x squared plus 1, which is 2x. Rewriting this, so we divide out the 2. This is x times x squared plus 1 to the power minus 1/2. Then we calculate the second order derivative, so f double prime of x. F double prime of x, we have a multiplication x times x squared plus 1 to the power minus 1/2. So we apply the multiplication rule. We first derive x, so this is 1 times the second part, x squared plus 1 to the power minus 1/2, and then plus x times the derivative of the second part, which is minus 1/2, x squared plus 1 to the power minus 3 over 2 times 2x. This then becomes x squared plus 1 to the power minus 1/2 minus x squared times x squared plus 1 to the power minus 3 over 2. If we then want to take out a common factor, you could say that this minus 1/2, this is 1 minus 3 over 2, and now we can take out a common factor x squared plus 1 to the power minus 3 over 2 times x squared plus 1 to the power 1 minus x squared, or this is just equal to 1, so this is x squared plus 1 to the power minus 3 divided by 2. We then go for the third derivative. Third derivative based on the last expression is minus 3 over 2 x squared plus 1 to the power minus 5 over 2 times 2x, or it is minus 3 times x squared plus 1 to the power minus 5 over 2. We can calculate the fourth derivative, so you can verify this yourself. But if you calculate the fourth derivative, you obtain 3 times 4x squared minus 1 times x squared plus 1 to the power minus 7 divided by 2. And if you like, you can continue doing this. But what you see is that you have no global formula in this case. So it is impossible to write this as a single expression, this nth derivative as a single expression. So clearly, not every nth derivative of a function can be written as a simple expression, as a one-line expression that defines this nth derivative for every value of n. So sometimes it's just impossible to write it as a single expression.